Okay, so today we're going to look at that's recording. Formation of color complex. Before I explain why transition metals form colors in their ions, this is one thing that students always get confused. They think that transition metals are colorful. The metals itself are not colorful. It is the ions. Okay? Like your copper 2 plus, which is blue color. Iron Fe2 plus, which is green. And Fe3 plus, which is brown. So it is the ions of the transition metals. And that's one of the properties actually of the transition metals, where the ions form, where the ions are colorful. So before we look at the explanation as to why colors are formed, we need to look at the orbitals first. So the learning objective is to sketch the shape of a 3D XY orbital and 3D Z square orbital. Now I find this rather hard because in the previous syllabus, you are expected to draw all 5 orbitals. Somehow, this year they just want you to draw 2. But I don't trust them, okay? You will learn to draw all 5. Because it's you already learned how to draw GXY. You might as well draw GXZ, GYZ. Define and use the terms degenerate and non-degenerate orbitals. Before I explain degenerate and non-degenerate, I would just like to show you a bit cut off. I would like to show you how the orbitals are arranged based on their energy level. So starting with 1s that you cannot see at the bottom, it means that it has the lowest energy level, followed by 2s, 2p, 3s, 3p, and etc. Now you see 2p subshells. There are 3 orbitals. Each box represents orbital. Each orbital can hold 2 electrons max. Okay? P subshells contain px, py, and pz. I don't know if you still remember the shape. It's like it contains lobes. Okay? It doesn't matter where it goes, px, py, pz, because they have the same energy. That's why they are drawn on the same line, same level. Okay? This is what we mean by degenerate. Px, py, pz are degenerate, have the same energy. Likewise, for 3D orbitals here, 3D subshells, we have 5 orbitals. We will look at the orbitals shortly. All these 5 orbitals at this moment are degenerate because they are at the same energy level. So degenerate means orbitals that have the same energy. The opposite, which is non-degenerate, is of course the opposite meaning. The orbitals that have different energy level or different energy values. Example, 3s and 3p orbitals are non-degenerate. 4s, 3s, even though they're the same subshell, they're S-type, but because their position and energy level is different, they are considered non-degenerate. Okay, so I hope that explains the definition of degenerate and non-degenerate orbitals. Okay, orbitals that are all at the same energy level. Non-degenerate means orbitals that are not at the same energy level. At the moment, transition metal are d-block elements. That means the last orbital being filled is their d-blocked, 3D orbitals. So we want to look at basic orbitals specifically because that's what makes them different from the group 1, group 2 metals. Group 1, group 2 metals are called the S-block elements. They don't have electrons in the d blocks. Okay, let's start drawing. So these are the 5 d orbitals in transition metal atoms. First is the X, Y, dxy. Sometimes it's written as dxy, which is the same thing, the xy orbitals, xz, yz, x squared, y squared, and z squared. I will teach you how to draw later, but I would just like to describe, explain their shape. First, I will bring your attention to the one with the power squared. X squared, y squared means the lobes. So it kind of looks like your p orbital, but instead of having just one, you now have two lobes, four lobes, okay? Like a flower. Whereas p orbital is just a single shape is that? That's a single line. A single eight. Here you've got double eight, and they sit exactly on the x and the y axis. Well, before I forget, since they are in three-dimensional, instead of looking at just x and y, there's another axis that is diagonal or like coming up to you. So if this is x, this is y, z would be like that. Okay? Don't make fun of me, I'm not ultimate. So I will show that on paper, it's just drawn as diagonal, and I will write it as z. Okay? Right. So the x squared, y squared, you have the lobes sitting on the axis, but only x and y. Okay? Z stays clear. So this is the x squared, y squared. The next one is z squared. Dz squared is the odd one out because it's the only one who has just a single H, and there's a ring in the center. Okay, so if you look at the 5 orbital, z squared is only on one out. Okay, so that's easy to remember. And the power 2 indicates that the lobes are located on the axis. Okay, on z axis, not on y axis, not on x axis. It has to be on the z axis. Wherever your z axis is, it sits on that plane. Okay? xy, xz, yz, they do not have that power 2 in their letter, means that these lobes are sitting between the plane. Okay, so let's have a look at the first diagram. Not easy to see, but can you see that these lobes sit in between the y and the x axis? So we call this the xy. Okay, I'll teach you how to draw it in 2D later on. Okay. Diagram number 4. Looking at these orbitals, they are sitting between z and x. You see that? Z, x, and z axis. So this is the dx z. And last diagram, last drawing, it is sitting between the y and the z axis. So we call it the dy z orbital. Okay? So when they don't have the power in the letter, that means they sit in between this mentioned axis. Okay? So you will label that. Yes? Yes, sure. Okay, Ken. Oh, sorry. I didn't realize that. Ataupun Who's joining us, Sana? See, this is one. Hazwan. Hi, Hazwan. Okay, so you can copy the description and you can label them. Next, I will teach you how to draw the shapes of all 5 in 2-dimensional. Okay, in 2-dimensional drawing. Even though the learning objective only say to draw 3D xy and 3D z square orbital. Okay, so that is actually a typo. It's not 3D z2. It's 3D z square. What time does this lesson end?
9:55.
9:25. 25. Okay, remind me. Yes?
What is it that the
Z square, Y square?
yeah.
You know? British, beyond my knowledge. This is all the orbitals that have been found. I guess there are no orbitals that sit on the Z and Y axis, that's why it doesn't exist. I didn't make this up, by the way. This is actually discovered by by chemists back then. Okay, then move on. Are you ready to learn how to draw it in 2D? Actually, when you draw it in 2D, when you're given freedom, it's actually easy. Okay? The most difficult part is to work with their axis. Okay, can I move on? Right, so that's just to show you the 5 boxes represent this 5 orbitals. Again, I mentioned they are not in any particular position. Okay, one box can represent, for example, YZ here or XZ, so it's not a fixed position. Okay, 2D drawing. I will follow the one that we have up here, which is XY, right? The XY. So if you want to draw the XY, and given the freedom to do so, you will start with only X and Y axis. Okay? Yeah, the space connect, you just draw it on the space that we have on page 15. Even though the learning objective mentioned 3D XY and 3D Z square. Okay, so these are my 2-dimensional axes for now. By definition, my orbitals sit in between X and Y. Can you see that these orbitals are not sitting on the axis, but rather in between the axis? There's a difference between, yeah? That is sitting on the axis in red. Green is sitting between the axis. Yeah? Okay. That's done. That's my dxy already. The only thing that I'm missing is my axis, my other axis, not my x, which is z. Okay? So that's why I focus on the axis that I'm interested in first, okay? Which is dxy. Again, I remind you, this is only possible if you are given the freedom to label your own axis. Okay, but if they already fix your x, y, and z, then you have to follow the position of their axis. Okay, and then z square is easy. d z square. I can just choose whatever axis I want to use as long as I have z, maybe here x. Okay? So dz square is drawn as two lobes with a ring in the center. That's my dz square. I am missing one axis. Who am I missing? Y. So then you just draw y. Okay? Always leave the diagonal axis last because otherwise later you will get confused. Next is dx square y square. Same thing. X-axis and y-axis. This time I am looking at x square, y square, which sits on the plane, on the axis. That means my orbital will be on the line. So please take note of the difference between dx square, y square, and dxy. They're slightly different. Okay? The missing axis is my y. I just draw it diagonally. Sorry, z. Yes, thank you. I just draw it diagonally. Next is xz. I will make it smaller so that I can fit everything in here. Okay, I can follow so far? Okay. Next is xz. So I will prepare the x and z axis. Again, it doesn't matter how you label your x, y, and z. Y can be horizontal, x can be vertical, x can be diagonal, whichever. So x, z means my orbitals are between the x and the z axis. It does not touch, it does not sit on the x or z axis, nor the y axis. This is my dxz, and I'm missing my third axis, which is y. And lastly, I want the dyz. I need my y-axis and z-axis, and then you draw the orbitals to sit in between. And your missing x is x-axis. The missing axis is x. This is if you can choose your own axis, but if you don't get to choose, the axes are already drawn and fixed for you. You must follow that axis. Okay? Okay. Any questions so far? No? Can move on to the next one. Drawing shapes. Okay, that's basically in your syllabus. They only want you to be able to draw the x, y, and the z square. But what is the point? Because the others, well, you have to learn the others as well to understand how you draw the x, y. Right. So these are just explanations. So they explain about the lobes sitting on the axis, or the lobes. Okay, I shouldn't use the word lobes. This is how a transition metal atom would look like, or any D block elements, 3D block elements. This is only so far showing the d orbitals. If we're looking at copper, there is your s, 1s orbital, 2s, 2p, somewhere like that, 3s, 3p, which is a little bit bigger, I don't know what I'm doing, and then 3p, which is what we see here. Okay? So, it's not easy to see, right? It's not easy to visualize. But what I want you to get out of this is that an atom or an ion is surrounded by electrons. Okay? It is literally the electrons are moving in all directions inside the orbitals. So your concept of electrons orbiting around the nucleus is wrong. Well, that's the simplest explanation that they can give you to start off with chemistry. Okay? If they teach you this straight away, when you first did chemistry, then I can assure you, you will not want to do chemistry in B level. Okay? So this is almost half the truth of the half true about electrons, because electrons is actually not a particle, it's a wave.
Yeah.
So that's another line. Okay? So these orbitals are region, actually these orbitals are only probability of finding an electron. Right? You don't necessarily, because electron is not a particle, it's a wave. So that concept is a little bit difficult to understand. Okay? But what I want to, the key whole message here is that the elements, the metal ions, have electrons around it. Okay? And if you put ligands, for example, water, ligands must have no pair of electrons, right? Even though water is not charged, water approaching your metal center ion, whatever the metal center ion is, you can imagine the repulsion that is happening here. Okay, and that's only one molecule of water. Imagine having 6 molecules of water in 6 different directions approaching your metal center ion. So that repulsion actually has an effect on the position or the energy of the d orbitals. Okay, which we will look at next. Learning objective is to describe the splitting of the degenerate d orbitals into 2 non-degenerate sets. Okay? Some, depending on the shape of the complex, if we're looking at octahedral, there will be 2 higher energy level and 3 lower. As for tetrahedral, the 3 orbitals will be higher and the 2 orbitals will be lower. Okay, and then this one will be for later on. I don't think we will get to cover this. Why we see colors. Okay? Right, splitting of the orbitals. If my transition metal is an atom, don't worry about this. I'm just using this diagram to help you understand that sentence where in the presence of ligand, the basic bonds cause the part blah 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 to be non-degenerate. Okay? So this is the arrangement of the d orbitals in a transition metal that is isolated. Isolated means it is not attached to ligands, it doesn't form ions, it's just a metal on its own. Okay? The d orbitals are degenerate, same energy. But when you start bringing ligands to your transition metal, whether it's an ion or a neutral atom, repulsion is happening. Okay, repulsion from the electrons of the metal and the lone pair of electrons of the ligand. Okay, the repulsion will cause this d orbital to split into 2 groups. The first group is the one with the higher energy level, Okay? And the second group will be the lower energy level. Actually, they are all higher than this. Okay, it's just that not showing. Now this first group is the group that, if you notice x square, y square, that square is the orbitals that sit on the plane, on the axis, sorry. Okay, and then the second group is the orbitals that sit in between. Don't worry, I will, you have this diagram as well later on. Oh, well, you can start labeling them, but I have another diagram for that later. Orbitals in between axes. The idea is, both this group gets repelled by the repulsion. They feel the repulsion effect from the low pair of electrons on ligands and the electrons on transition metals. But this group that has a higher energy level feels more repulsion effect than the other. Okay? Why? Why is it that the orbitals that sit on the axis feels more repulsion? The idea is more repulsion, higher energy. Less repulsion, lower energy. Okay? Which is what you have also on page 16. Okay, so I'm going to explain the idea of placing ligands. So this is the best diagram that I can find on the internet. Let me just use this diagram first to explain, and then later on we will read the description or the explanation and see if you can understand. Okay? So this 6 balls, blue balls, I'm going to change it to red. These are your ligands, whether it's H2O or ammonia, whatever, whether it's neutral or charged, I don't care, but I know that they contain a lone pair of electrons, because that's the criteria to be a ligand. They can donate. In the center is my, say, Cu2 plus ion. Okay? And these represent orbitals. Okay? There is also, missing from this diagram, my axis. So I will just call this X, Y, and Z. Ligands in octahedral complex will approach the copper 2 plus on the axis. Okay? So if you imagine, I have ligands coming here on the one axis, on the x-axis and z-axis. Okay? The orbitals that sit on the axis will feel the most repulsion. Okay? Imagine, who are the 2 orbitals that sit on the axis? X squared, Y squared, okay? And then, sorry. Y squared, X squared, Y squared is this. And then I've got the other one, which is DZ squared, that ring at the center. So can you see that these orbitals line up with the approaching ligands? So the electrons will have a bigger repulsive effect compared to orbitals that sit in between the axis. They don't line up, they don't clash, they don't meet with the ligands. They will still feel the repulsion, just not as much. So this brings back to our idea of the orbitals that sit on the axis. They line up with the ligands on the axis, therefore they feel the most repulsion, hence higher energy. The orbitals that sit in between the axis will not meet the ligands directly. They will not meet, they will feel sahaja, but they don't meet because the ligands are coming on the axis. these orbitals sit in between the axis. Okay, so they only feel less repulsion, hence the energy is a little bit lower. That's for octahedral. Okay, so this splitting in energy for the d orbitals are now called non-degenerate because they no longer have the same level or same amounts of energy. And the difference between these two energy levels is called delta E, or the splitting energy. Okay? Because they are arranged in terms of energy, right? Lower energy, higher energy. The difference between that is called the delta E. So delta E, we will look at delta E later to explain why a certain color is seen. Why do we see blue? Why do we see red? Okay. So that's for octahedral. If you look at your notes, for tetrahedral, it's the opposite. For tetrahedral, the orbitals that sit on the axis is now lower, and the orbitals that sit between the axis will have higher energy. This time they feel the higher repulsion. Why? I will use this diagram first, okay? So this is how the four ligands are arranged around your mental center ion. Okay, so I'm just going to draw tetrahedral shape, and then your axis, X, Y, Z. Can you see now your ligands sit in between the axis, and they will repel the orbitals that sit in between the axis more. Okay, so if you look at your xy, x square, y square, it doesn't clash with your incoming ligands, right? Z square also doesn't clash. It will feel the repulsion, but it's not lined up together. Okay? So that's the reason why tetrahedral have the opposite group of orbitals compared to octahedral. I'll read the explanation later on. Okay, so I've already shown that to you. This is also mentioned. 3D orbitals before placing any ligands, 3D orbitals after placing ligands, where repulsion happens that cause your d orbitals to split. Okay? Initially they're degenerate orbitals, same level, and then with ligand approaching, repulsion happens, they split in a group of 3 and 2. Okay. This is also mentioned. This diagram is the one that you have in your notes, so you can label this now. For octahedral, it is the orbitals that sit on the axis that feel the most repulsion, which is your dx square, y square, and dz square. As for the orbitals between the axis, feels less repulsion. That's your dxy, dyz, dxz. Okay? For tetrahedral, it's the opposite. Dx square, y square, and dz square, which is the orbitals that sit on the axis, feels less repulsion because your ligands are not coming along the axis, they come in between the axis. So your orbitals between axis feels the most repulsion. Okay? So you have no, yes, haven't talked about that. Okay. But the groups will always be the same. Okay, the one that sits on the plane comes together. The one that sits in between the plane will go together. It's just the position, different position in octahedral and tetrahedral. Okay. And what? Next is the explanation. You see the electrons in d orbitals that are nearer to the lone pair of ligands have more repulsion, hence higher energy. So just remember, whoever is closest or whoever feels the most repulsion will have higher energy than the ones who are not directly aligned with the lone pair of ligands. Okay, so for octahedral, electrons in the dz square and dx square y square line up exactly with the lone pair of the ligands, okay, where they form the dative coordinate bonds. The electrons in the dative bonds repel the electrons in the dz square and dx square y square more than dxy, dxz, and dyz. Repulsion increases the energy of these two orbitals more than the other three. Can you understand that? Okay? Basically, it's just wording different, it's just worded differently from how I have explained it. Okay? But the idea is the same. For tetrahedral, this time, it's the dxy, dxz, and dyz that line up exactly with the ligands, which is in between the axes. So they are the ones that feel the most repulsion. Therefore, these three orbitals will have higher energy than the two orbitals. Okay. That's a lot for you to digest. But you probably don't have to follow word by word, verbatim, as in the one in the notes, as long as you understand why some orbitals have higher than the others. You understand the concept of the orbitals aligned or line up with the ligands, hence more repulsion, then that should be okay already. Okay? Okay, so that is all for today. I will not go on to the next one because I think this alone is already too much. Okay, so please make sure you try to read this again. Try reading through the explanation in the textbook if you don't understand my explanation now. But don't just brush it off. Okay, and just hope that this question will not come up, or if it does come up, you're going to skip that. Okay? Okay, so that's all for today. Okay, you can go, everyone. Thank you. I'll go bring this stuff.